Hello, I'm Katie Alvis. I'm currently an undergraduate student studying computer engineering at Michigan State University. This summer I had the opportunity and privilege to work at Rochester Institute of Technology's Munsell Color Science Lab under Dr. Susan Barnett. The research I will be presenting on explores how to determine the representative color of a multicolored image. This study, that is still ongoing, investigates how a person averages the color of a multicolored image or object within an image. Meaning, when an individual is shown the picture of something, what color would they say best represents the image as a whole? Through this study, the context of what object the individual is seeing is slowly revealed to mitigate predispositions of remembered color. In this study, we gathered a group of 25 images of various objects and sceneries that came in multiple sizes and image qualities. A majority, 18 to be specific, of the pictures we had were red, green, and orange tomatoes, but we also included 2 blue skies, 1 patch of grass, 1 patch of sand, a patch of skin, a panel of wood, and a pile of sliced green peppers. One application specifically tied to the tomato and green pepper images is in the realm of color science and agriculture, where the color of an agricultural product is regularly a grading factor in determining the type, taste, or quality of that product. The other images allowed for a broader color spectra to be covered and ensured that if a pattern of selection were to be found, that it would be consistent across multiple image sources and objects. The first objective was to systematically remove the context of the images while retaining the color variety within the objects in the images due to specular highlights, shadows, and any other imperfections. We wanted to take away any biases towards a color choice that may arise from having seen the object or a similar object before. We were trying to prevent people from claiming the color of what they wanted to have seen rather than what they actually saw. To do this, we began by cropping the images into 768 by 768 pixel squares. This was the size that fit in the images we gathered and cut out backgrounds or other objects so that the viewer would only see the object itself. From this crop, we wanted to further reduce the quality of the image to remove more knowledge of what the image could be of. We thought about simply resizing the crop of the image down to 64 by 64 pixels, but this method uses nearest neighbor averaging or similar tactics to decrease the number of pixels, which could ultimately create colors that had never even existed in the original image. We also thought about, but decided against, taking an even smaller crop of the image. Doing this, we would lose the highlights or shadows or other imperfections that provided the potential for differences in opinions of the best color representation. Instead, we decided to grab every 12th pixel of the 768 by 768 pixel image to artificially create a 64 by 64 pixel version of the image. This method allowed us to retain the variety of colors within the image and to not create colors not previously present. We repeated the same process, this time grabbing every 48th pixel in the 768 by 768 image to create a 16 by 16 image. After creating the reduced quality images, we still felt like the clusters of lighter pixels and darker pixels may be ignored by people assuming correctly that they came from reflection and shadow from the light source when the image was taken. With this in mind, we decided to shuffle the pixels of the 16 by 16 pixel image randomly to create a completely scattered version that had shadowed pixels next to illuminated ones. With this, we were left with 5 different images for every original image. The full original image, a 768 by 768 crop, a 64 by 64 reduced image, a 16 by 16 reduced image, and a scrambled 16 by 16 image. We wanted to show the viewer one of these images and then have them choose a color that best represented the image as a whole. So then came the task of generating a list of color choices. With the images we had created in mind, we wanted to systematically develop a way to grab color choices for the viewer to select from that were 1. Represented within the image they saw, and 2. Still differentiable. Wanting to provide the same list of color choices for each of the 5 images we created from the original to investigate whether the context changes a person's choice, we decided to work with a 16 by 16 reduced size image whose colors were present in every image. We wanted to see if an individual would be most drawn to the most saturated pixel in the image they had just seen, the most chromatic pixel, or if they were able to take a true average of all the colors represented in the image. From this, we were able to grab 3 color choices. We then decided to divide the 16 by 16 image into 9 sections and again grab the most saturated, most chromatic, and an average from each section. This sectioning method came from the thought that having an image flash for only 1 second may prevent someone from being able to really look at the whole image. Someone may be drawn to a particular segment of the image and not have time to process and interpret the rest. From these saturated colors, chromatic colors, and average colors, we created a list of at most 28 colors for the user to choose from. In this particular picture, some sections had the pixel that was the most saturated be the most chromatic as well, so we were left with only 25 colors to choose from. Knowing that we wanted to reduce the options down to 9 color choices to prevent people from feeling overwhelmed or not taking in all of their options, we were able to tackle the next problem of some of the color choices being too similar. To do this, we established a base delta E threshold of 2. Delta E 2000 is the current accepted perceptible distance between two colors, taking into account the lightness, chroma, and hue values apparent in C-Lab color space. Basically, delta E 2000 tells us how similar two colors are and allowed us to discard any colors that would look too similar for an observer to be able to tell apart. We made sure to hold on to the average of the whole image, the most chromatic of the whole image, and the most saturated of the whole image, as those were the colors we were most interested to see if a participant was drawn to, but we removed colors from the remaining 25 one by one that caused the most conflict, meaning the colors that were within 2 delta E between the most number of choices. We did this until there were no colors in conflict and all had a 2 delta E difference between each other. In some cases, the delta E threshold was not enough to reduce the number down to 9, so we would increase the delta E threshold until closer to 9 choices remained. Then we removed the color choices that were farthest in lightness from the average color of the whole image until only 9 remained. In other cases, in the more uniform images generally, this delta E threshold reduced the number of color choices down to below the 9 choices we wanted to provide. This introduced a new problem of artificially creating more colors. We ended up taking an average between each of the remaining colors and then testing the average's color difference until 9 options were created. Having created the images to be viewed and the color choices to be selected from, the last step in the setup process was to actually create and organize the experiment. We decided the best order was to start by showing the viewer the scrambled images and then slowly work backwards to reveal the context that we had previously hidden. This meant that we would randomly order the 25 scrambled 16 by 16 images and test those first. Then randomly order the 16 by 16 reduced size images and test those, followed by the 64 by 64, 768 by 768 crop, and finally the full images. The given image was flashed on the screen for 1 second, and then the user was presented with color choices. These options were arranged in a 3 by 3 array with gray spacing in between to prevent one color from affecting the interpretation of another. These arrays were scrambled randomly every time so that a user wouldn't remember based on location what color they chose last time for the image if they pick up on the pattern that they had seen a version of the same image before. Once the option was chosen, the viewer would be shown a gray screen for 1 second before being flashed another image. This was to allow them to readjust and reset before they were asked again what they saw. This process was repeated for all 125 images, and data such as the color, location, and reaction time were collected to provide insight into any patterns that may occur on specific images or by specific participants. As I mentioned before, this project is ongoing, and we don't have all the data yet to draw any strong conclusions as to what pattern people follow when trying to find a representative pixel color for a multicolored image. However, I do want to mention that we already have planned some future work to build upon and solidify the conclusions we hope to draw from this experiment. One limitation that we are facing now due to remote work is that every participant has to use their own PC to run the experiment. This may have an effect on the way colors are displayed and the color that someone may choose because of it. Whether the participant is sitting inside or outside, the weather that day, or the lighting in the room may all have an effect on their answers. In the future, beyond the pandemic, we hope to rerun the experiment in a controlled environment on one screen. This secondary experiment would serve as a guide for the validity of remote matching experiments in color science. We also want to expand on the images that are tested to push beyond the color science and agriculture application.
To wrap things up, I'd like to send a huge thank you to Dr. Susan Farnian, Catherine Carpenter, Dara DeMaw, Anku, and all the other members of RIT's Multicolored Science Lab. Thank you for taking me under your wing this summer and teaching me all about the world of color science. Also, I want to send a thank you to you for listening to and watching this presentation. If you have any questions about anything that I talked about or didn't talk about, please feel free to leave a comment down below. Thank you.